What a pleasure. I'm now joined by Barish. Barry, welcome.
Hi.
Thank you very much for taking the time to talk to us today.
Oh, happy to do it.
And first of all, of course, congratulations on your award. It must have been very exciting to win.
Very exciting to win, and it's a big party to go to Sweden, so I've done that. Now I'm back to regular life.
I bet it is. Now, so you're doing the Kavli lecture for this year's conference. Give us a little bit of an insight into what you'll be talking about.
Well, the work that I do is got to do with gravity, and it has to do with a prediction of Einstein in 1916, which is that gravity, like electromagnetism, has waves. 100 years later, we saw them. So my lecture is simple. It's what are gravitational waves? How did we detect them? And what good is it? Not good for application, but what good is it for moving science forward?
Now my first question, this might sound like a bit of a silly question, but my first question is what went through your mind when you discovered these waves? Bearing in mind what you were talking about with Einstein, and bearing in mind that the black holes collided all these billions of years ago, what went through your mind when you were successful?
You know, some of my colleagues would have the simple answer, a eureka moment. I panicked. So we saw something that looks like it's supposed to look like gravitational waves. For me, it happened in our detectors, which are in Louisiana and Hanford, in the middle of the night, so I was sleeping. But when I got up, my email was full of all this stuff. And looking at it, it looked like gravitational waves. But then the first question is, how are we fooling ourselves? Or how are we being fooled? And resolving those questions to my satisfaction, and a lot of our satisfaction, took a month or so. So maybe this quite eureka moment didn't quite happen that way. But everything that we did kept looking better and better. So it was good. And then it turns out 4 months later, we saw a second example. And that's confirmatory, and then everything's been kind of a nice ride since then.
What are the implications of this?
The implications are totally scientific. The gravitational waves are incredibly weak. That's why it took 100 years. But it's two scientific reasons, other than establishing that Einstein has a pretty good theory of gravity. The first is how good. And that is, in order to study what gravity is really like, you want to study it where it's strongest.
Right.
There's nowhere stronger than in a black hole. So now that we have these black holes that we can detect, we can study, is it really Einstein's theory in detail? Is it alternates? There are alternative theories. How does gravity really work in the strongest field? Maybe, how do we reconcile gravity with quantum physics? So that's the physics part. Equally interesting is the following, that, you know, I'll reflect back. Galileo in 1609 put together some lenses which are made for our eyes, and made the first telescope to look at the sky. He looked at Jupiter and saw 4 moons. And that was the beginning of modern astronomy. Now look at what we know 400 years later. It's a little presumptuous, but in a sense, we've done the same thing with a totally different way of looking at the sky, things that have to do with gravity instead of electromagnetism. And that is, we've seen the first peak at looking at phenomena that are a result of gravitational effects, the collision of stars, or gravitational effects. So we've seen two different types already. We've seen black holes collide, and we've seen what are called neutron stars collide. Neutron stars colliding are a totally different phenomenon. It's nuclear physics in the most extreme conditions possible. So the science is very different than that. So it's all pretty exciting.
So if you've seen the first peak, what's the next peak? What's your work go on to now?
Oh, we're a little bit, again, like the telescopes. Galileo's telescope wasn't capable of what we're doing now. And so how do we make more sensitive devices that can see what we see now in more detail and see other phenomena that'll give gravitational waves? So whenever I'm not, being interviewed like this or giving a talk or something, we're trying to make the detectors better. And we know how. maybe not just turning a knob or something, but we know that we're not limited by nature itself. We can make more sensitive detectors. We have to develop the technology and improve the technology and solve problems. They're difficult, but it can be made much better. So we should be able to start making not routine, but lots of observations in the coming decades with gravitational waves.
Final question is, at your lecture and at this conference, there's a lot of young people here, a lot of young physicists, and you obviously remain very excited about your work. How important is it to imbue these young physicists with that same sense of adventure?
You know, I was once a young physicist. The problem is you get so much work to do.
Right.
As a young physicist, it can turn you off. Science is fantastic. It doesn't matter whether you make a discovery. We got lucky and made a discovery, but just the process of doing science, thinking about science, being able to conceive of something that people haven't measured before and doing it, or an idea that people haven't had before. And as students, you tend to get maybe bogged down by the necessary parts, which you have to learn how to have the tools to do the science. So it's not so different from musicians, where they spend a lot of time practicing and practicing in order to get the ability to actually do the profession well. So my advice to young students is keep your dream as in your foreground, but don't jump to it. You have to learn the tools. You have to learn the science itself, and
Barish,
you'll have fun.
Thank you very much indeed for joining us, and again, many congratulations.
Thank you.